Proof by counter example that the statement if p is a prime number, then 2p plus 1 is also a prime number. So prime numbers, let's just take few examples. So for the subdivision, the prime numbers are what? 2, 3, 5, 7, 11, etc. It goes. If p is a prime number, so when p is equals to 2, what will be my 2p plus 1? That is 2 into 2 is 4, 4 plus 1 is 5. So that satisfies the condition. This is also a prime number. 5 is also a prime number. When p is equals to 3, what happens to 2p plus 1? 2 into 3 is 6. 6 plus 1 is 7. 7 is also a prime number. So when p is equals to 5, what happens? 2p plus 1 will be 2 into 5 is 10. 10 plus 1 is 11, which is again a prime number. When p is equals to 7, what happens to 2p plus 1? 2 into 7 is 14. 14 plus 1 is 15, which is not a prime number. Therefore, by counter example, that the statement is not true. Counter example means we can just show or prove by taking any one of the examples. Even if any one case is not satisfying the condition, which means that the statement is true. So in this case, when p is 7, 2p plus 1, we got it as 15. 15 is not a prime number. So therefore, by counter example, the statement, if p is a prime number, then 2p plus 1 is also a prime number, is not valid, is not true. Now for the second part of this, use proof by exhaustion to prove that if n is an integer, then 5n square plus n plus 12 is always even. Few things that you need to know. Proof by exhaustion. Proof by exhaustion means you need to consider all the different cases. You need to show all the different cases. Now here we are talking about integer. N is an integer. So these integers can be classified into odd numbers and even numbers. Now we need to show that all the odd numbers are even. For this condition, 5n square plus n plus 12, and all the even numbers are also even. So we know the standard form. The standard form of odd numbers is 2k plus 1. And standard form for even numbers is 2k. Now, we need to prove for both of these conditions that this is always even. The equation given is 5n square plus n plus 12. Let's take the case for odd. N is 2k plus 1. So 5 into, instead of n, 2k plus 1 the whole square. Instead of n again, wherever we have n, you just replace it with 2k plus 1 plus 12. This is what 5 into 2k plus 1 the whole square is 4k square plus 2 into 2k, that is 4k plus 1 plus 2k plus 1 plus 12. This is 5 into 4 is 20, 20k square plus 5 into 4 is 20k plus 5 into 1 is 5 plus 2k plus 1 plus 12. Simplify this further, we will get 20k square plus 20k plus 2k is 22k plus 5 plus 1 is 6, 6 plus 12 is 18. So this can be written as 2 into 10k square plus 11k plus 9. So we know that anything multiplied by 2 is even. Anything multiplied by 2 is even. Therefore, it is even. So we are multiplying this function with 2, and we know that anything multiplied by 2 is even. Same thing we need to do for even numbers. For even numbers, we know the condition is n is equals to 2k. So 5n square plus n plus 12. Wherever we have n, replace it with 2k. So 5 into 2k the whole square plus 2k plus 12. 2k the whole square is 4k square plus 2k plus 12. Now this is 20k square plus 2k plus 12. We can take 2 common outside. 2 into 10k square plus k plus 6. So same like the previous, we know that to prove that something is even, we need to take 2. We should have 2 as common outside. So we know 2 multiplied by anything is even. Therefore, it is even. So proof by exhaustion, all the different cases, all the cases that we have to consider. So we are talking about integers. Integers are of 2 types, odd and even. So 1, 3, 5, 7, all of them till infinity, 1, 3, 5, 7, 9, 11, 13, 15, etc. All of them comes under. If we prove that odd integers are even, then we have finished half of the numbers. And then even numbers, we know the standard form is 2k. So for even numbers also, we prove that in this case, it is even. So for that, the only thing is 2 should be common outside. So this was from algebraic proof. Hope you have understood this. If you have any doubt, feel free to write it in the comment box. Thank you for watching.